Okay, welcome to the second digital lab, lab number 5, at least at the time that I'm recording this, that's what we're calling it. And I just have to do a little bit of a disclaimer, and that is that I just taped 25 minutes of lecture and then somehow lost it. The iPad just crashed and I lost my lecture. So I had already written some of the notes, so I'm going to try and reproduce it and make it clean. It'll probably be better the second time around because I've already said it once. I got a little practice. Anyway, let's move on. So this lecture, this lab, I'm sorry, is about digital electronics. When we started digital electronics, we talked about the parts of a computer. So let me just go to the parts of the computer. Like I said, I had already discussed this, so there's a lot of stuff on the screen. But basically, right, the parts of a computer, we've got the keyboard, which is already in yellow. And the keyboard is an input device to the CPU, which holds the logic and the power supply and some memory. And of course, there has to be power. There's usually some kind of external or permanent storage. And there's some kind of output device, right? A monitor, a speaker, etc. So these are the parts of the computer these are the things that make up a computer. And what we're basically talking about in electronics is what goes inside the CPU. And we talked about the logic functions, the building blocks of logic functions, starting with the basic AND, NAND, OR, gates, etc. And so what I wanted to talk about today is go a little bit further in and talk about memory, right? In order to get information into and out of the logic gates, you've got to have memory. Two kinds of memory actually, right? That there's both volatile memory and storage. Right? Volatile memory is the active memory that brings things in and out and remembers them for maybe just only a short time. It can remember it for a long time too, but it's made to be really quick access, super quick access, bring things in and out, as opposed to storage or permanent memory, which takes a lot longer to access, is also a lot more permanent, doesn't require power in order to save it, right? It may be mechanical or magnetic, and you can turn it off and save the information. But it also takes longer to access it. The volatile memory, the active memory in a computer, the RAM, for example, the random access memory, is the high level memory, the stuff that's remembering information from the keyboard that then sends it into the computer, that's remembering it in the computer to send it through the logic, and that's remembering it, storing it until you need it to send it out to the output device. So we're talking about volatile memory pretty much today. And with the volatile memory, what we want to talk about is the very basic building blocks, again, of volatile memory. Actually, let me pause a second. Talk about three basic things and a fourth connected thing. Three basic parts of memory. One is called the very basic thing is an SR latch. It's a memory bit. It remembers a single bit of information. We are then going to talk about how we create a bit of actually, I'm not sure which comes first. We're going to talk about how we create a bit of information, and how we'll use an SR latch in order to what's called debounce a switch. We'll talk about that in a second. Give me a moment. We'll then talk about clocked memory, which is timed memory, a synchronous memory, and which is called a flip-flop. And then slightly more complicated is the shift register, which is it really is the building. We're using the SR latch and the flip flop to build up the shift register, and that's where we're really showing how we're bringing bits into the computer, saving them, and passing them on to the logic in the computer. So these are the things we're going to talk about today. Really, for this lab, we've really only got 4 basic circuits that we're building. It's not so bad. Okay, so, but the first question before we ever get to the memory is I do want to talk about how do we create a bit, right? Actually, let me go back here and just think about really when we're talking about memory and bringing information into and out of a computer, how do we physically do that, right? Well, physically it's an electronic signal. But what we're doing, just think about hitting a single keyboard, right? Hitting a single key in a keyboard. When you hit a key in a keyboard, what it does is the computer then generates a number between 0 and 255. We talked about that in the last lecture. It generates a number between 0 and 255 and turns it into, or in binary. In binary, that's 8 bits. Hence the, let me sort of highlight where we are. So that's 8 bits, right? So a single keyboard hit creates 8 bits. So if I hit the Z key, the M key, the N key, whatever, it is encoded in 8 bits of information. Those 8 bits of information are zeros and ones, right? I just randomly created an 8-bit piece of information right here. I don't know which key on the keyboard this is. I could challenge you to go and figure out which key on the keyboard that must be. I don't know. I didn't figure it out. Okay, but what that does then is let me erase and redraw this arrow, right? So what it does is it sends those 8 bits into the computer. Every time you hit a key, it sends 8 more bits in. But it doesn't send them in, well, if there's 8 wires, it sends them in at the same in parallel. But if there's a single wire, it sends them in one at a time. So the computer needs to read one, remember it, read the next, remember it, read the next, and remember it. Okay. So this is where we're talking about the high-level memory or the volatile memory, right? It's going to read in these bits, it's going to remember it, it's going to send it through logic. Okay, how do we create these bits, right? That was the question before we even talk about the latches and flip-flops and registers. How do you create a bit? Remember that a bit is a 0 or a 1. It is also represented as a low or a high. See, now I can fix my errors before you ever see them, but I didn't. So what is a bit? A bit is a 0 or 1, right? It's a binary digit, right? It's 0, 1, and right, this is the 1's place, this is the 2's place, this is the 4's place, this is the 8's place, 16's place, etc. Okay, but a single bit is just the 1's place, a 0 or 1. Or it's the digit that goes in a decimal place, sorry. It can be represented, 0 can be represented as low or off, or in electronics, it's represented as ground, right? 0 volts. Ground is 0 volts. The 1 is a high bit. It's an on. It's a switch that's on. And in electronics, we typically represent that as 5 volts. Now be careful. We're talking about most digital electronics does run on 5 volts, but not all digital electronics does, and so it may be a different voltage, but it's typical to run digital electronics on 5 volts. So the high bit, or the 1, is represented by 5 volts. I did mention in class once that sometimes instead of 5 volts, to make your life easier, 0 volts would just be a short to ground, whereas 5 volts would just be an open circuit. You don't actually even need a power supply because it could just be an open circuit. But that is only for certain families of digital logic. In particular, the one that I know of is TTL logic, transistor-transistor logic. Transistor-transistor logic expects an open circuit for high and a short to ground for 0 volts. So you don't need the 5-volt power supply. But not all logic families. And when we say families, we mean a type of chip that's manufactured in a certain way. And it's all the chips in that family, right? All the AND gates, NOT gates, etc. in that family. So TTL is just one type of family. In general, they all accept 5 volts is high and 0 volts is low. So if we don't know if we're using TTL, we should be using 0 volts and 5 volts, not 0 volts and open circuit. And in particular, if we're simulating a circuit, it's typically, unless you know that you're using a TTL simulation, it's going to be 0 volts is your 0 bit and 5 volts is your 1 bit. Okay. So that's the discussion about how do you create a bit. How do you create a bit? Therefore, you're switching between 0 and 5 volts. What do I mean by switching between 0 and 5 volts? Well, if I want to create a bit, for example, if I want to just manually create a bit, I'm going to take a power supply and I'm going to have a ground and then the hot wire from the power supply, right? The black wire, well, it doesn't matter. It depends on what we're doing, but we're going to have a ground wire and we're going to have a hot wire, which we can set at 5 volts. And we're going to switch between them. If I want to put a 0 bit in, I'm going to make sure that we've grounded the input. If I want to put a 1 bit, we're going to make sure that the input is 5 volts, and we've got to switch between them, physically switch between them. There's something funny, something a little unusual that happens with switches. Now, I don't know about unusual or funny, but something that happens with switches that you may not realize is that, now, okay, let me take a step back and say, remember that what a computer is doing is reading zeros and ones. It's reading ons and offs. And it's reading them very, very fast, right? A computer that works at a gigahertz is doing 10 to the 9th operations per second. That means that it can read 10 to the 9th bits every second. So when I'm sending in those keyboard strokes, right, it's reading them a heck of a lot faster than I'm sending them in, because I'm only sending in 8 bits every time I hit a key. But it can read 1 billion bits every second. So it's reading them awful fast. So I got to be careful about making sure I'm sending it the bits that I mean to be sending it. And what I mean by that is, if we're switching between 0 and 5, when I hit a key on a keyboard, I'm turning something on and turning something off, right? When I let go, it's off. When I push it, it's on. And that on is actually creating 8 on-offs in the meantime. But there is something that I'm sure you've all experienced before, and that is when you turn a switch on and you turn a switch off, sometimes there's a little bit of an indeterminate state. Right? So just think about the typical light switch, right? So the typical light switch, that when you turn on a light switch, sometimes the light flickers a little bit before it makes good contact. Sometimes you hear a little bit of sizzling, zzzt, or zzzt, inside the light switch when it's trying to make good contact, right? It doesn't make physical, solid contact until you really turn that switch on. So what that actually does is it sends a signal. When you switch the switch, the signal that goes from 0 volts to, with a light switch, it's going to be 120 volts, right? Because it's home power, 120 volts. When you turn that switch on, it's actually going to vary a little bit between 0 and 120. It's going to go zzz, it's going to go 0, 120, 0, 120, 0, 120, zzz, 120 until it turns on. That's called bouncing. Switches physically bounce. They make the electricity before and we should talk about the time scale. Typically, the time scale may only be milliseconds. With a light switch, you've seen it before. It might be a second before you push it all the way up, and it may probably not a second, but half a second before you make a good contact. But it may be a few milliseconds. For a few milliseconds, it's trying to make good solid contact, and it bounces a little bit. It bounces between its low value and its high value. So that's really bad for digital electronics. Bouncing is bad for digital electronics. Because what happens is when it bounces, it's basically sending a bunch of zeros and ones that you didn't mean to send. Let's say you just meant it was off and you were sending a 0, and then you turn it on and you just wanted to send a single 1. But when you turn it on, it bounces up and down 3 times. You're not bouncing the switch physically, but the power bounces a little bit before you make solid connection. And so it by accident sends 3 bits instead of 1 bit. 0, 1, 0, 1, 0, 1, 0, 1, 1. I guess it wouldn't be a 1, 1. It would just, well, anyway. So what we need to do first, one of the things that we need to learn to do in electronics is what's called debouncing a switch. Right, so we need to debounce a switch. We need to be able to send zeros and ones and be sure, be very determinate about that state, and that we don't get any bouncing. So we're actually going to, so what we're going to do in this lab today is we're going to talk about the SR latch, which is a very, very basic building block of memory. Basically, it remembers its state. You put it in a state and it remembers its state. And we're going to actually use the SR latch to see how we debounce a switch. We're going to debounce a switch by using an SR latch. And then we're going to look at the flip-flop, which is a clocked memory bit. The SR latch is a non-clocked memory bit. What that means is you put in the information and it reads it, and it determines its next state. Okay, so let me say that a little bit more clearly. An SR latch is a memory bit. You can set its state, and it's going to remember its state, and you can change its state by putting in more information. So its next state is going to be determined by what its current state is and what the new information you send it is. And that's just going to happen when you put the information in. As opposed to a flip-flop is a clocked bit. And what that means is that a flip-flop, it'll remember its state, and then you put in more information, but it won't change state until a clock tells it it's time to change state. Why is that important? Well, that's important. Clocked logic is really important because, again, your computer works super fast, right? 1 billion operations per second, more than 1 billion operations per second. So how does the computer know when you're sending information and when you're not? How does the computer know? I mean, it's doing 1 billion different things at once inside the computer, and so how does it know when to send the next bit on? What it does is a computer has a clock, and that's sort of one of the most important things inside the computer is it's got a clock, and it will only do the next operation when that clock strikes. And what I mean is like a ticking clock, tick, 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 tick. So it'll do an operation on every tick, not during the tick. It'll do the operation at the start of the tick. And then it'll wait until the next tick to do the operation, to pass a bit on, let's say. And let's just say the bit passes on in, almost infinitesimal amount of time. Certainly, if the clock gets so fast, then we have to worry about the speed of light. And are we waiting? Are we not giving enough time to travel from one place to another, given that the information travels at nearly the speed of light? But anyway, that's beyond what we're talking about here. So the clocked bits are ones that don't pass the information through until a clock strikes. So it's got to have an input for a clock. So the SR latch is not clocked. It's not synchronous. The flip-flop is a synchronous or timed bit that doesn't pass information through until a clock strike. And the shift register is just a more complicated set of flip-flops that saves a bunch of information at once and allows you to change it one bit at a time. So those are the things that we're going to do today.